Hi, welcome to our video for lesson 1.3 on conditional probability. Now recall that last week we learned how to use relative frequencies to define probabilities. So for example, if I randomly selected a U.S. Senator in the 113th Congress, which is our current Congress, I could determine what is the probability that the senator is female. If there are 100 total senators, and right now there are 20 of them that are female, then I can find the probability, the probability that a senator is female by taking the number of female senators divided by the total number of senators, and that gives me the probability of randomly selecting a female senator. But suppose I want to answer this question. If I randomly select a Democrat U.S. Senator from the 113th Congress, what is the probability that the senator will be female? Now there are 53 Democrat senators. 16 of those Democratic senators are female. So the probability that I have a female if they're a Democrat is equal to 16 out of the 53 senators, and that gives us 0.302. So what I've found is that although there's a 20% chance of selecting a female senator overall, when I randomly select under the condition that the senator has to be a Democrat, then the probability of selecting a senator was 0.302. And this is the idea behind conditional probability. I condition on one event. That the senator is a Democrat, and find the probability of another. That the senator is also female. And another way we would write this notation-wise, just to make it a little bit more simple, would be to write the probability that they're female given the condition that they're a Democrat. So this brings us to our formal definition of conditional probability. Conditional probability tells us what is the probability of event B given that event A definitely occurs. We use the notation P of B given A, and this is the formula we use to calculate it. We have the probability of B given A is equal to the probability of A and B both occurring divided by the probability of A. Let's try to gain a little intuition about this. We'll use this Venn diagram. Now the probability of B occurring if A occurs. If we know that A occurs, it means that we can eliminate all of the sample space that's not included in A. And the chance that B would occur if A also occurs is going to be equal to this little portion over here where B and A intersect, divided by this restricted sample space of A. So for example, if we're looking at A as being a Democrat and B as being female, then we know that there are 20 female senators, of which 16 are Democrats. So we'd have 16 in here. And 4 female senators who are not Democrats, that leaves. And we know that there are 53 Democrats. 16 of them are also female, which leaves us 37 Democrats who are not female. Of a 10, we have 43 senators left over that are neither female or Democrats. So if we want to find the probability of being female, given that someone's a Democrat, that'd be the probability of being female and a Democrat, 16 over 100, divided by the probability of being a Democrat, divided by our 53 over 100, gives us the 16 out of 53, which is 0.302, that we found before, just using our intuition. So we can see that this formula makes sense and it works. Okay, so let's do a little practice here. So this is what's called a contingency table, a two-way table that breaks down the current U.S. Senate by political party, and I just broke it into Democrats and others because there are a couple of independents also, and some Republicans, and by gender also. So you can see we had 37 male Democrats. Whoop, excuse that. 37 male Democrats. We had 16 female Democrats for a total of 53 Democrats. We had 43 other party males, 4 other party females, for a total of 47 people from other parties. We had a total of 80 males, 20 females, and 100 total senators. So take a minute and pause the video and try to work through, find the probability that a randomly selected senator is male, the probability that they're male given that they're a Democrat, the probability that they're a Democrat given that they're male, and the probability that they're a Democrat given that they're not male. So please pause it for a minute and turn it back on once you've had a chance to try these. Okay, so if we come through here, we can work through these now. Probability that someone is male is 80 out of the 100 total senators. This is 0.80. The probability that someone is male given that they're a Democrat. Probability that they're male given they're a Democrat, there are 37 male who are male and Democrat out of 100, divided by there are 53 Democrats out of 100, gives us 37 out of 53, which is 0.698. The probability that someone is Democrat given that they're male. So again, we need to figure out there are 37 males who are Democrats. So the chance of being male and a Democrat is 37 out of 100. The probability of being male is 80 out of 100. This gives us 37 out of 80, which is 0.463. So I just want to make the point right now that you can see that the probability of being male given that you're a Democrat and the probability of being Democrat given that you're male are not the same thing. So just keep in mind the probability of A given B is generally not equal to the probability of B given A. That's important to remember. And let's take a look. The probability of being a Democrat given that you're not male. Let's see. So if you're not male, that would be female. We've got 16 out of 100 who are not male and Democrats. We've got 20 out of 100 who are not male. That gives us 16 out of 20, which gives us 80%, 0.80. So we can see that the probability of being a Democrat is different depending on whether you're male or female. The last thing I want to talk about is called the multiplicative rule. The multiplicative rule can be found just by rearranging this definition of conditional probability. If I multiply both sides of this equation by the probability of A, I can find the probability of A intersect B is equal to the probability of A times the probability of B given A, and equivalently, it's also equal to the probability of B times the probability of A given B. This is the multiplicative rule. It's how we can find probability of an intersection A and B. We'll do a quick example. Suppose that 88% of UVM students have smartphones and that among UVM students who own smartphones, 68% of them are iPhones. What is the probability that a randomly selected UVM student owns an iPhone? This is another time when you could stop the video and try to work it out on your own before taking a look at the solution. Okay, so let's solve it. So let's let A be the event that they own a smartphone. We'll let B equal the event that they own an iPhone. We're told that the chance that a student owns a smartphone is 88%, so 0.88. And we're told that the probability that they own an iPhone, given that they own a smartphone, is 0.68. So what's the probability that a randomly selected UVM student owns an iPhone? Well, that would be the probability that they own a phone, and it's an iPhone. We can find this by taking the probability that they own a smartphone and multiplying it by the probability that the phone that they own is an iPhone, given that they own a smartphone. This is 0.88 times 0.68, and it gives us 0.5984. That'd be our answer. I hope this is helpful. That brings us to the end of our video. Thanks.